Yeah, so chapter 8 is going to be all about chemical equations, chemical reactions. We're going to look at some types of reactions later on, but today we're just really talking about what a chemical equation is, what the rules for writing a chemical equation are, and how we can balance it. So what is a chemical reaction? A chemical reaction is the process where one substance is changed into a different substance. So we did a whole lab on this at the beginning of the year with physical versus chemical changes. Some things, like when we melt wax, it's still wax, or if I boil water, it's still water when it goes through that process, because when it condenses it becomes water again. Chemical reaction is really more where you're getting something brand new. Like if I burn paper, I started with paper, I ended up with ash. Cooking food, cooking eggs, you're getting a totally new substance when you cook it. One thing to keep in mind when we're doing equations, the reactions we're always going to put on reactants we're always going to put on the left-hand side, and products will be on the right-hand side. Sometimes you might have like a double arrow if the reaction can go back and forth, but for the most part we're going to be looking at this for now. And finally, just a drawback to the conservation of law of conservation of mass. Remember, everything on the left-hand side will have to be equal to everything on the right-hand side. It just might be rearranged. So, if I had 7 carbons on the reactant side, I'm also going to have 7 carbons on the product side. They just might not all be in the same arrangement that they were before the reaction. So a chemical equation does represent, with symbols and formulas, both the identities and how much of a reactant or product that I have. What's nice about chemical equations is they tell us 2 things. They give us not only the molecular values, but also the molar values. So if I look down here, we just had a test on this, but that's kind of a wild formula there, NH42Cr2O7. Thankfully, they give us the name for it up here, ammonium dichromate. Hopefully you kind of recognize NH4 as ammonium. Maybe dichromate we haven't seen as much, but that is ammonium dichromate, and that gives us nitrogen gas, chromium 3 oxide, and water on the product side. So you can see, if I look at it, I've got 2 ends on the left, and I've got 2 ends on the right. I've got 4 times 2 H's on the left, and then 4 times 2 H's on the right. 2 chromiums on the left, 2 chromiums on the right, and then 7 oxygens on the left. There's 3 oxygens here, and the 4 in front of the H2O tells me I have 4. So that's a total of 7 oxygens on the right. Does counting the atoms make sense? How I can see that there's... So then, what these numbers are telling me is, for every... There's no coefficient in front of this, or this. So that tells me there's 1. So for every 1 unit of ammonium dichromate, I get 1 molecule of nitrogen, 1 unit of chromium 3 oxide, and 4 molecules of water. So that's at the molecular level, but this also tells me that there's for 1 mole of ammonium dichromate, I get 1 mole of nitrogen, 1 mole of chromium 3 oxide, and 4 moles of water. So those coefficients tell us 2 different things. Sort of like how molar mass tells us both the formula mass and the molar mass, that number. Oops. So we know in the lab, we're going to do a lab where we look at some evidence for chemical reactions. Note that not all these things necessarily mean a chemical reaction is taking place, but they're good indicators of it. For instance, like I keep going back to boiling water. Boiling water will produce a vapor, and it'll start to bubble. But that's not a chemical reaction. That's a physical change. But production of a gas can be evidence of a chemical reaction. Just like as we did or are going to do in the magnesium oxide lab. You burn magnesium, and you see that some heat and light are given off in terms of energy. That's a good indicator that a chemical reaction takes place. You don't have to burn something, though, to see that. If I just put sodium hydroxide in water at room temperature, you're going to start to see that get hotter and hotter as heat forms during that reaction. And then the formation of a precipitate, I mean, if you mix 2 clear liquids together, solutions together, and it comes out blue or it comes out yellow, that's usually a precipitate being formed. A precipitate is just a solid that drops out of the solution. So if you've got 2 solutions, mix them together. We're going to do a lab on this too. We're going to see some precipitates form from mixing solutions together. And finally, like I said, color change. When you see things rusting, that's a good indicator of a chemical reaction. When you have a different color, and you didn't just like paint over it. So those are kind of the big 4 that you're looking for if you're determining. Not all those things have to happen, but each of those kind of provides a clue that we can assume a chemical reaction is taking place. So some rules for writing chemical equations. Number 1, we can't just make up a chemical reaction. Like, it actually has to be something that occurs. So the equation must be factual. It also must contain the correct formulas for reactants and products. And finally, the law of conservation of mass must be satisfied. So let's just look at an example. Earlier in the year, we broke down water into its components using electricity. If I have H2O, it breaks down into hydrogen and oxygen. I think that's a fact, but do you guys know what's wrong with hydrogen and oxygen there? Do we know something about those 2 things that I might need to change? They always come as something. Let's see if this rings a bell. They always come as a pair. There's certain diatomic molecules, and this is how we got distracted by bubble tea, because I guess, did I say 6? I meant to say 7 if I said 6. But there's a mnemonic device to remember these 7 elements that are always diatomic, because they have no fear of ice, cold, and it's out of order. But I learned it as have no fear of ice cold beer, but I probably shouldn't be, using that with you guys. So I noticed on Google they have the bubble tea. It's like National Bubble Tea today. So if you want to remember it as have no fear of ice cold bubble tea, play a little game there. I'm gonna pause this. But yeah, But honestly, yeah, you can say have no fear of ice cold beverage of your choice. But I honestly, for me, the thing that helps me remember it is if I go to P table. I know hydrogen. I just get used to hydrogen being H2, but then over here, there's kind of this right angle that forms of the other 6. So like if you start at nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. That's actually the way I remember it. Is it's just this like corner on the periodic table along with hydrogen. So whatever way helps, but either way you do it, those all do have to have a 2 as a subscript because otherwise your molecular formula would be wrong. But that's not the only thing wrong with our equation. Because now I have to look at the third thing, the conservation of mass has to be satisfied. If I look at my hydrogens, I see there's 2 hydrogens on this side, 2 hydrogens on this side. But if I look at oxygen, I only have 1 here, and I have 2 here. So can I just do this? Can I just make it H2O2? Does that look like something I can do? Now it's balanced. But is that factual? Did I start with... Do you guys know what H2O2 is? Hydrogen peroxide. Did I start with hydrogen peroxide when we did that experiment? No. So I can't just change the subscripts. I have to change something else. I have to change the coefficient. So we make that 2. But now that ruins my my hydrogens because now I have 4 hydrogens here. Or I only have 2 here. So what if I put a 2 there? Now I have 4 hydrogens on each side. And I have 2 oxygens on each side. Because this coefficient, just like the parentheses do, this coefficient goes to both the hydrogen and the oxygen. Like I said, we'll do plenty of practice with that. So that was just kind of a preview of what's to come. By the way, just to note, most of those diatomic molecules are gases at room temperature, but bromine is a liquid and iodine is a solid. So we're going to start with writing word equations and eventually get into formula equations when we balance. But these facts that are represented, we could say like methane and oxygen are yielding carbon dioxide and water. And this is actually something you guys do in a lot of labs. Do you know what this, do you know where you might see this? What do you have on your lab station that you can turn on? Bunsen burner. Yeah, whenever you light the Bunsen, light the Bunsen burner, you're providing a lot of oxygen and heat to, or you kind of, I shouldn't say heat, you're providing a spark to get this reaction going, and then that methane combines with oxygen to form CO2 and water. What I can do is I can turn that into what's called a formula equation, and now that takes all my words and turns them into formulas. So methane actually has a formula known as CH4. Oxygen gas is still O2. Carbon dioxide and water vapor, which is H2O. Notice this equation is not balanced, but that turns our word equation, which was qualitative, into a formula equation, which we're going to make quantitative. So finally, those are my first 2 steps. You have the word equation, which you don't have to write the word equation out every time. But in your head, you should know these substances are reacting to form these substances. Get the formula of each of those. That step is probably going to become 1 at some point, because when I think water, I think H2O. When I think oxygen, I think O2. Even when I think methane, personally, I think CH4. And you might get to that point eventually. But when you write a correct equation, the law of conservation of mass must be taken into account. And we're going to do that by balancing the equation. So the amount of reactants and products must be adjusted so that we have the same number and type of atom on each side. So here's my equation. We're going to count atoms on each side. So as it stands, before I put that 2 in there, I've got, if I look at carbons, I've got how many carbons on each side? I have 1 carbon here, and I have 1 carbon here. Hydrogen, when I started, I had 4 hydrogens on this side, and only 2 on this side. But if I put that, so that tells me I have to double this. So if I put this 2 here, now I have 4 hydrogens. I've got 2 oxygens on this side. I've got 2 oxygens on this side, but then this 2 gives me 2 more oxygens. So I've actually got 4 oxygens on the right side. What can I put here in front of the O2 to make it balance on the left side? I need 4, well, I have 2 oxygens here. I have, remember, 2 oxygens here. So what do I have to do to this? Yeah, let's put a 2 in front, and that'll make it 4 total on the left side. So that's what I do if I'm not sure where to start. I just start with the atom on the left, count how many carbons you have on each side. If it's good, go to the next one. Count how many hydrogens. If it's good, go to the next one. If it's not, fix it. We'll look at some examples. Plenty of examples, balancing equations. But you can see they walk you through in the next slide how to go through that process to eventually get to where we got with CH4 plus 2O2 gives me CO2 plus 2H2O. And again, you got it. That's the Bunsen-Burner reaction that we're seeing there. And just so you can visualize it, notice this was CH4. It became CO2 on this side, but we had 1 carbon, 4 hydrogens, 4 hydrogens, 4 oxygens, 1, 2, 3, 4 oxygens. Just some symbols you often see in chemical equations. The single arrow, the best way to say that, I think the most common way would be to say yields, because there's different ways to obtain products in different chemical reaction, but yields pretty much covers it all. Reversible reactions, meaning they can go back and forth, can be shown with double arrows. And then these ones, the S, you might not have noticed those, but there were little parentheses after all these telling me whether it was a solid, liquid, or a gas. All those G's in that equation meant gas. L obviously means liquid, and S means solid. One that we might not be familiar with is AQ. AQ means aqueous, it's dissolved. A lot of our chemicals actually come in solid form, but for the purposes of our lab, I will dissolve them in water and give them to you. So you might think they're liquid at room temperature, but they're actually a solid dissolved in water. Like if I gave you salt water, and I said this is salt, you might think salt is a liquid, but it's actually just a solid substance dissolved in water. Just be kind of mindful of that. Most of the time, if I'm giving you solutions, especially if you know it's an ionic compound from before, it's in a solution form, that doesn't mean it's liquid. That means it's just a solid dissolved in water. So I'll tell you, if it's aqueous, that's what I mean. Some other symbols. The up means that you have a gaseous product. You don't always necessarily see that as often. Sometimes you see heat or a triangle written above the arrow. That means that I had to heat up the reactants to get them to actually react with each other. There's not enough energy at room temperature for them to react, but when I heat them up, they react. I can also note what pressure, or if I had to increase the pressure to get that reaction going, or same with temperature. And then finally, sometimes we use a catalyst to make the reaction go faster. For instance, manganese dioxide. It's this really black substance that gets all over the place, but we do use it in one of the labs. It will help actually speed up the reaction, and we can indicate that by writing it over the arrow. Again, that's a catalyst. And then E for electrolysis. So let's look at our first sample problem here. They want us to write a word equation and a formula equation for sodium oxide added to water, forming sodium hydroxide. So first off, we can just write that out. We've got sodium oxide is added to water, and it forms sodium hydroxide dissolved in the water. Does the word equation make sense? Does that represent the facts we're being given? So now let's make that a formula equation. Sodium oxide. Sodium is Na, oxide is O. Are they perfectly balanced? Na has a charge of +1. Oxygen has a charge of -2. Let's make it Na2O. Good. And what did they say? What form is it in? It's solid, right? So let's put an S to represent solid. Water at room temperature. It's important they said at room temperature because what state will the water be in? Liquid. Sometimes I make a cursive L so you don't think it's a 1. And then finally, sodium hydroxide. Hydroxide is OH minus, so it's going to be NaOH. And do we know a symbol for sodium hydroxide dissolved in the water? Should be AQ. Everything makes sense so far? So this is not balanced, I don't believe, because I have, if I count up my atoms, we have reactants, we have products. Sodium, I see 2 on the left, 1 on the right. Oxygen, I see 1, 2 on the left, 1 on the right. And then hydrogen, I see 2 on the left and 1 on the right. So it seems like it's going to be a really simple fix here. If I just stick a 2 in front of that, now I've got 2 sodiums, 2 oxygens, 2 hydrogens. I wish they were all that easy, but they get a little tougher than that one. Yeah. Any questions on this? Okay. So sample problem B.